Welcome back, viewers. I hope the Form 5s were able to get an answer to that question. The question, which was, describe how lightning occurs between a negatively charged cloud and the ground. Mr. Mkonda, I hope your students were able to get the answer right.
Let's see what they have for us.
Okay, one has said a negatively charged cloud will induce a positive charge on the ground. A large PD develops between the cloud, and the ground. Then a spark occurs. This answer is from 78708748. Are they on the right track?
Yeah, this one I think he must have if dropped in my mark guide because he's giving the exact answer that I have.
Oh, that's even better. That's nice. Well done.
Yeah, it's quite good. Your answer is correct, and you've explained all the points that need to be covered. So let's just recap on the answer together. So the negatively charged cloud, as we have been instructed, will induce a positive charge on the ground. Those are important things that need to be mentioned. The positive charge is induced on the ground. Now we have the negative and the positive. So between the two, there's a large potential difference that has been developed. Now electrons or negatively charged particles move towards the ground in a form of lightning. So a spark would be formed. So the answer was correct. So I hope we are all ready to go through questions on that. We'll find more probably on your past papers as well. Now let us move on to electrical resistance. Again, here we will lay down the ground for us to proceed. There are things that we need to look at. We're talking about electric charge. It will be needed there. So charge can either be negative or positive, as we have said before. The negative is of course the electron, and the positive would be the proton. Charge can be measured. Charge is measured in coulombs. So charge can be measured in coulombs with the symbol capital letter C. Now the amount of charge that passes through a point per second is now referred to as current. How much charge passing through a point in a second is called current. And then charge can be calculated by this formula. Current, which is measured in amps, multiplied by the time, and the time must be in seconds. And then we can write it in symbols as Q is equal to IT. And in order for the current to exist, the current that we're talking about above there, in order to exist, there must be a potential difference in the circuit, like we've seen in the thunder there. PD, of course, what is this potential difference? It is the electrical energy supplied per coulomb of charge flowing through the point. As we have said, the charge must be supplied with energy to pass through, and this is measured in volts. I think this would now lead us to the next part, where we now look at the insulators and the conductors. So we have what we call electrical insulators. Materials that we can have can be an insulator, electric insulator, or an electric conductor. What is this insulator? In an insulator, all the electrons are attached to their atoms and will not move on their own. So the electrons are not easily to move on their own. But on the other side, the conductors, some electrons are free. So those free electrons and are able to move freely inside the conductor. So the electrons here are able to move freely through the conductor. So if you have the atoms, the electrons are able to move freely through the conductor there. Now, as the electrons are moving, there's going to be an opposition to their motion. So the opposition to the flow of the charge is called the resistance, which is what we're going to be discussing in detail today. What is this resistance? The symbol for resistance, of course, is capital letter R. When current passes through a conductor in a complete circuit, there's going to be a voltage drop between the points in the conductor, and this voltage drop can be measured. The better the conductor, the smaller the voltage drop will be given off. So there's less voltage drop if the conductor is a good conductor. Now, if the current through the conductor is I and the potential difference across the conductor is P, then its resistance R is defined by resistance is equal to potential difference divided by current, where R is equal to V over I. You can also play around with the mathematics there to change the subject of the formula. Resistance is measured in ohms with the symbol omega. Now that we've got that, let us look at the types of resistance. So we're going to look at two types of resistors. There is what we call a fixed resistor and a variable resistor, illustrated of course in my diagram there. So the resistors that we've got here, this one is a variable resistor, which means the resistance can be changed, it can be varied. This one is a fixed resistor, so we have just one known resistance that we've got. We cannot change this resistance, yet in this one the resistance can be changed. And then we are going to be looking at the relationship between the current flowing through a resistor and the voltage across the resistor. So in this next part we're going to be discussing the investigation of a relationship between PD across the resistor and the current through the resistor. So the current moving through the resistor, the potential difference is across. So we're going to be using these components here. We are going to have your cell, of course. It could also be a power supply. You're going to have your switch in this part. Then you have your connecting wires. Then we have our variable resistor. We have our ammeter to measure the current. We have our voltmeter to measure the voltage. We also have our fixed resistor in which we are measuring the current and the voltage drop. So the variable resistor will vary the current passing through the resistor there. Now I have some typical results that I'm going to talk about. So in my case, we're talking about the potential difference here. So our potential difference and our current. So in my case, I have a potential difference of 0.3 when the potential difference was 0.3, or rather I think it sounds better if we start with the current. So when the current is 0.04, the potential difference is going to be 0.3. When there is a 0.08, the potential difference was 0.6, and the list will move on. Now we're looking at the relationship. How are these things related? Look at the tool that we've got. So I have a current of 0.4, I have a PT of 0.3, current of 0.04, excuse me, and a potential difference of 0.3. Now look at what is happening. The current is increased, so we're increasing the current now. So if we're increasing the current, we've got the voltage. The current increases to 0.08. What happens to the voltage? Interesting. The voltage also increases. So what do we notice? The relationship here is showing us that these two are directly proportional. But now if we take the voltage and we divide by the current, we are going to get a value here. So if you say V is equal to, we are looking for, in this case, we want to calculate what we call the resistance. So if you say R is equal to V over I, and then we take your 0.3, you divide it by, let's get our 0.3 clear there, 0.3 divide by your 0.04, and I got 7.5 ohms. But if you look at all these values that we're getting, they are all giving us the same result. What does it show? So this shows something very interesting. It shows us that the voltage and the voltage divided by the current in a fixed resistor is constant. So if we take a plot of these results, so if we take our results as we have them there, we plot these results in a graph, this is what we'll be getting. So we're going to get a straight line that passes through the origin. So the values will be a straight line there. And this shows us the proportionality of the voltage and the current. The gradient of this graph will give us the resistance. So if you take the gradient as your V over I, it will give you what we call the resistance. And this line being of this nature, it shows us that it shows us that the gradient is constant. So it also implies that the resistance is constant. Hence our 7.5, hence our 7.5 that we obtained from the other side there. Now the relationship V is equal to IR here is called Ohm's law, and it can be verified in this graph. So this graph is verifying Ohm's law. It is proving Ohm's law, which is V is equal to IR. Some of us are asking ourselves, teacher, where is this V is equal to IR coming from? And yet you've talked about R is equal to V over I. Now if you do your mathematics, you make V the subject, so you are going to have your V is equal to IR, which is your Ohm's law. So the resistance R is constant. And please note, resistors with such a behavior are called ohmic conductors, or conductors with such a behavior are called ohmic conductors. Which are those? The ones that have a fixed resistance. Now, what are the factors that affect resistance? Let's quickly go through the factors that affect resistance. What would the resistance depend on? Resistance depends on a number of things, but we're just going to look at a few. Temperature is one of them, but amongst those, we have the type of material. What material are we using will determine the behavior of the material, the substance, according as far as its resistance is concerned. So the nature of the wire, for instance, some metals allow an ease to the flow of current than others. For instance, copper has a very low resistance, and it can be used in wiring and in other things there. The factors also, we are looking at the nature. There are some pure metals. Okay, maybe there's too much information here. No, was. Let's just skip this one and go through some of these metals which have a high resistance. So some metals have high resistance. For instance, your metals like tungsten, your constantine, and your nichrome, they have high resistance, which means they don't allow a free flow of electrons like your copper, as we have said. So in this case, we are saying good conductors have a low resistance and poor conductors have a high resistance. I'm going to skip this one. Maybe we don't want to have an information overload.
Yes.
So we are moving on. Let us move on to the next factor. The next factor is the length. The length L of a resistor. How does the length affect the resistance? Of course, the length does affect the resistance. The longer wire has a higher resistance than a shorter wire. Or the longer wire or longer conductor has a higher resistance. Now, resistance in this case means it is directly proportional to the length. If I increase the length, so if I have the length and I have the resistance, if I increase the length, it means the resistance is also going to increase. So these two are directly proportional. For instance, my wire S and my wire T. Wire S is made of the same material as wire T. It has the same cross-sectional area. The only difference is just the length. So this one would have a high resistance compared to the other one there. Then we also have the cross-sectional area. The cross-sectional area also has an effect on the resistance. What is the cross-sectional area? So if you look at this one, it is thicker. This one is a less thicker compared to the other one. So the thicker wires have lower resistance than thinner wires of the same material. So the material is the same, the length is the same, but this one is going to have less resistance than that one. So we are now saying resistance is inversely proportional to the cross-sectional area. So if I have my cross-sectional area here, then I have my resistance. If I increase the cross-sectional area, the resistance will decrease, which means that is inversely proportional. I hope we are together. Maybe it comes to that point again, where you need to answer a question. So I have a question for you learners at home. Now the question I have here is about resistance. So let's go through the question. The question is, you are given a diagram. It shows a circuit diagram with a battery, which is a combination of cells, EMF, which is the electromotive force of 6.0 volts, a wire of length 0.5. So the length of the wire is known to be 0.5. It's connected across points A, B. So the wire is connected across those 2 points. Now there is a current of 2.4 amps that is passing through. So there are things that are given here. We're given the voltage, we're given the current, we're also given the length, the resistance, or the length of the wire. Let's see what the questions are. We need to calculate the resistance of the wire. The wire is replaced with the wire of the same material of length 1.5. So the answers that we are expecting here would be the resistance of the wire is going to be 2.5 ohms from your R is equal to V over I. The resistance of the longer wire will be greater, of course, because we increase the length, and it would be 3 times as greater. Now, as I can see, you want to say something.
Yes, sir. And unfortunately, we've run out of time, but we'll just give you a little bit of time just to wrap up. Just say your summary, because I can see there that you have a summary. So I'll give you just 1 minute to wrap up, sir.
Thank you very much. We've come to the end of our lesson. What have we covered? Let's just quick reminder. We've talked about lightning, and lightning happens due to the discharge of cloud, due to a charged cloud inducing a charge on the ground. So we have a negative charge inducing a positive on the ground. The negative charge on the cloud is attracted to the positive charge on the ground in a form of lightning or a large spark. Resistance, which also talked about resistance, is the ability of a conductor to prevent charge from passing through. The resistance of a wire is proportional to the length and inversely proportional to the cross-sectional area. I hope learners at home and Nogwazi,
Yes.
you've admired the beauty of physics.
I don't know about me and physics getting back together again, but we'll see. Mr. Mkonda, sir, your students have questions. I'll just ask two questions. One says, for the lightning conductor, why is copper the only metal that is used?
Okay, that's a good one. I mentioned copper as one of the metals that can be used for the reason that copper is a good conductor. So in this case, what should be happening is we need something that will have an ease of flow of current. So we need to conduct the current downwards there. So we talked about the conductor. So copper is one of the best conductors that we've got. That is the reason why copper is used.
Okay.
Could have been any other metal, but copper is the better conductor of electricity. So it's a better metal that we can use.
All right. And the second question is, what is the function of the copper wire, and why are we not using other wires?
I think it's these guys are very interested in this topic. The
Yes.
function of the copper wire is to do what we call earthing. Remember when we talked about charging by induction. So we want to discharge. So when we are discharging, we are taking down the electrons to the ground. So the function of the copper is that it has to be a conductor, because here the electrons can freely move. And we can use any other conductor, of course.
All right.
Yes.
Mr. Mkonda, thank you very, very much for being with us. We hope you're going to join us sometime soon to continue our physics lesson.
Yes, we hope we'll meet again in another discussion on a very interesting subject, which is physics, and also always emphasize, guys, let's admire the beauty of physics.
From Fives, I hope you heard that, Mr. Mkonda. Thank you very much. We'll be right back right after this.
Hands come in all shapes and sizes. Indeed, one of God's greatest inventions. It is amazing.
Welcome back, viewers, and unfortunately this is the last lesson of today.
That was the last lesson.
Yes. Good afternoon.
Yeah, a very good afternoon. We had a good day today. How was your day?
It was fantastic.
Yeah.
eh?
My mind is a bit blown away by physics. I mean, it's been a while since I did physics, so I'm a
So you
bit-
did physics.
I did physics, but it has been a long time. Like you heard before, physics and me are just not okay.
Okay. Thank you very much. Please give us today's timetable.
Tomorrow's timetable, you mean?
Oh yeah, tomorrow. Sorry.
Yes, so tomorrow, brace yourselves. We'll start with science for grade 7, which is from 2 until 2:30 p.m. And then we have Eswatini for from 3, which is from 2:30 p.m. until 3:08 p.m. Then we have science for from 3:08 p.m. until 4:45. Then we have mathematics for from 5, from 4:45 until 4:25. Then we have chemistry for from 5, from 4:25 until 5 o'clock. So I hope you guys are ready for that. And please do remember that since it was a holiday, today we were doing Friday's timetable. So tomorrow we're going to do today's timetable.
Oh yeah, Nogwazi. And the lessons for today are available on YouTube. So if you've missed any episodes, don't worry, we got ya, guys.
Yes.
We got ya.
Yes, we got you. And please do not forget to subscribe on our YouTube page so that you're able to get notifications, and to also watch on our Facebook page as well. And do not be afraid to ask us questions on WhatsApp. like I said, I cannot emphasize this enough. Please do not call us. Just text us and we'll further your questions onto the teachers.
And
Alright.
one more thing, guys. Please stay at home.
Yeah.
Do not be like my Shombe. Stay at home.
Stay
Please,
safe,
and
guys.
stay safe.
Yeah. So we'll see you guys next time. Bye.